called stellar evolution or the life and death of stars. Starting off is the emission nebula. It is created after the death of a star, otherwise known as a supernova, when it explodes. Then we have a hot emission nebula. After the nearby stars surrounding the emission nebula heated, hot gas clumps will start to clump together into bigger clumps, and then the protostar will form after the clumps of hot gas collapses in upon itself. And how big and how massive it gets depends on how much gas it has collected. And it can lose 50% of its mass while trying to become a real star. And then after a couple million years, you have the T-Tauri star. And so the T-Tauri star is still young, and it is extremely unstable. It pulsates because of the heat and gravity. So the heat will want to push out, but the gravity will want to keep it in. So then it looks like it'll be pulsating. And then you also have the jets that shoots from its north and south pole. And then an accretion disk will form, made up of gas, dust, and rock. And an accretion disk is just the disk formation it makes, made up of the material it has within it. So then at this point, when the star has matured more, it can turn into one of these 4 different types of stars. On the left would be the brown dwarf, in the middle, the red dwarf, to the right is the yellow dwarfs, and bottom middle is high mass star. So the brown dwarfs, they are the smallest type of stars, only 13 to 80 times heavier than Jupiter, and they have the longest lifespan of all stars. So the reason I put debatable for both of them is because brown dwarfs are actually in between the range of being called a planet and a star. So some scientists call it a really hot Jupiter. Others would like to call it a failed star, but most of them call it a brown dwarf. And the longest lifespan, why I put debatable there, was because they don't die. So it's really debatable whether you can say if they have the longest lifespan or just they don't have a lifespan. And then you have the red dwarfs. They are the most common type of star in our galaxy. Around 70% of all stars are red dwarfs. They'll burn for about 10 trillion years, and their mass range can go from 7.5% to 50% of our sun's mass. Then the red dwarf death. They will expand into a red giant, and then they'll go supernova, and then in the core will be a white dwarf. That's all that's going to be left after it goes supernova. The yellow dwarfs, or mid-sized stars, depending on how you want to call it, they make up about 10% of our stars in the Milky Way. About 70% to 115% is the mass range, and our own sun is a yellow dwarf. A yellow dwarf death, it would become into a red giant, just like the red dwarf. It will release its outer layer, and then it'll become a planetary nebula. So as you can see up here, it'll make cool formations like those over here, I guess. And then it will contract back into a white dwarf. The high mass stars, they burn extremely fast. They live only for a couple million years, and they are hot enough to make iron. And then what I mean by hot enough to make iron is stars are made up of hydrogen. So the heat from the stars force the atoms to make into heavier elements. And then the heavier elements go on and on and on until you get iron. The largest star we know is UI Scuti, which is 1,700 times larger than our sun's radius and 21 billion times the volume of our sun. To really put that into perspective, if our own sun was 73 feet, UI Scuti would be 24 kilometers. So it's really big. The high mass star death, these stars will contract instead of expand like the yellow dwarf and red dwarf. They expand, this one contracts. They can either become a neutron star or a black hole. The neutron stars form when the core of the high mass star is 114 to 300% of our sun's mass, and then the black holes form when the core is about 300 to 1,500% of our sun's mass. So the black hole death. There's two particles that pop into existence, a pair, a particle and an antiparticle. They go towards each other and they cancel out like they never existed. So when one particle is on the inside of the black hole and the other one's on the outside, when they want to go towards each other, the one that's inside gets pulled into the black hole, and then the other one actually goes outside of the black hole and becomes a real particle. So what this means is you're adding mass to the universe that's not supposed to exist. So that makes the energy and the mass of the black hole actually shrink. And Stephen Hawking discovered this. He named it Hawking radiation. The neutron star death. These stars actually never die. They cool down until you have a ball of cold gas. Fun fact about these guys, there's 3 variations of them. The normal one would spin 700 to 1,000 times per second. They're about the size of a city. And there's the quasars, the pulsars, and the magnetars. Quasars they shoot jets that face away from us. Pulsars are ones that shoot jets towards us, and magnetars have really, really powerful magnetic field. Thank you for listening. If you have any questions, please feel free to ask me. And this is the end.
Is it true that they think that in most galaxies there's a black hole in the middle of those galaxies?
Yeah,
in most of the galaxies?
It's called a supermassive black hole. We don't actually know how they got there, but they are like the beginning of galaxies. Yep. Yeah.
With all your experiences this past summer, is there, did it influence what you want to study, or is there something that you got out of it that you, want to investigate further?
Well, I did learn a lot of this from my Johns Hopkins University experience. So I actually really enjoyed this. So I decided to put what I learned into a Google Slides so I could present it out to the community. Yes?
Explain a white dwarf again.
A white dwarf, so white dwarfs appear when the red dwarfs go supernova, and all that's left is the core. The core would become the white dwarf. The core is the white dwarf. And it's the same thing for a yellow dwarf too. Yes.
What's the white dwarf like made out of?
I know it's made out of heavier elements because it's the core, but I don't exactly know what it's made out of. Yes.
Do you know what happens to it after time? Does it just stay there for forever, or does it disband?
White dwarfs, they burn, they will die. I'm pretty sure it's definitely longer than the red dwarf. It's like an insane number, like 1 quadrillion. Yes.
So, when the red dwarf dies, the white dwarf becomes. What happens when the white dwarf dies?
When the white dwarf dies, it'll just cool down just like the neutron star. Yeah.
Mm-hmm.
There's no big explosion. Is that it?
Good. All right.
Thank you.
Thank you, Matthew. We're very excited about Matthew and his opportunity that he's going to have in the next, year and a half probably?
Mm-hmm.
Well, let's go.
Summer.
If through
Next
the
summer, yeah.
Yeah. And so I can honestly say, for 13 years old, I am really impressed with this kid. It's amazing where he's been and where he's going, and he's only been part of the club for what? A little over, maybe a year and a half.
And a
he came
half,
here? He
yeah,
was like
yeah.
11 or 11 and a half, something like that when he
Yeah.
first started coming here.
Uh-huh.
So, yeah, we'd like to think we had something to do with fostering his interest in astronomy.
Of course.
But we're really excited for Matthew. And where is Larry Crary? Larry?